Good morning, everyone. So today is the last lecture of Chapter 5. We are going to cover three-dimensional free body diagrams, three-dimensional equilibrium equations, constraints, and statical determinacy or indeterminacy. Okay, so if you remember Chapter 5, we have discussed about rigid bodies, 2D equilibrium conditions, 2D equilibrium equations, free body diagrams. So now we are going over the three-dimensional system, right? So what are the objectives of today's lecture? To identify support reactions in 3 dimensions and draw a free body diagram in 3 dimensions. And also to apply the equations of equilibrium, right? So that is the objective of today's lecture. And as you all know that everything in this real world is 3 dimensions, right? But for our ease of analysis, we make our assumptions and we convert 3-dimensional objects into 2-dimensional objects, right? So that we can do the analysis in short amount of time, right? But in actual, everything is in 3 dimensions, and we need to use 3-dimensional analysis if we need to do a, correct analysis. Okay, so with that, what are the applications? Let's talk about applications, right? So in this picture on the left side, you can see a ball and socket joint, right? If you happen to have a look at different, mechanical equipments, different machines, you must have seen this ball and socket joint. And on the right side, you have a journal bearing, right? So these are the examples, 2 examples of a 3D joint or a 3D system or a 3D rigid body, right? So this ball and socket joint, what is it doing, right? So just by looking at it, we can visualize and we can see what's going on. So this ball and socket joint, basically the base is acting like a support, and it's preventing the move in the vertical direction, right, and horizontal direction, right? So it's restricting the move in X, Y, and Z, all 3 directions, right? Now, if you look at the right side, the picture on the right side where we have a journal bearing, so what this journal bearing is doing, this journal bearing is restricting the move in X direction, restricting move in Z direction. But if this is the Y direction, let's say if this is the Y axis, then the shaft inside or the bar inside can move along the Y direction, right? So this support, this type of support, which is called a journal bearing, it restricts the move in 2 directions, but it allows the movement in 1 direction, right? So now the purpose of solving or analyzing 3D objects or 3D bodies is to design the joints or bearings, and we need to know about the support reactions, and the joints and loads must be determined, right? Okay, so let's move forward. Let's talk about support reactions in 3 dimensions. So we have already seen the support reactions in 2 dimensions, right? So table 5.2 of your book has more details about the support reactions, and there are so many support reactions, so many types of supports which have different support reactions. So here we will just have a look at 3 of those, right? So first of all, this number 2 on the top left, you can see a smooth surface support, right? So any object just resting on the surface, any surface, let's say ground surface, right? So this guy is resting on the surface, right? So what is this surface, or the surface is acting as a support, right? So what is this support doing? It's just restricting the move in one direction, that is the vertical direction, right? So this this object or this body or this member can move in horizontal direction, right? But not in vertical direction. So that's why there's only one reaction, this guy, in vertical direction, right? Now, if you look at this number 4, on the top right side, we have a ball and socket joint, right? So as we saw in the earlier slide, the last slide, that it restricts the ball and socket joint. So this kind of support restricts the move in all three directions, right? So that's why we have all three support reactions, that is Fx, Fy, and Fz. So we have restriction in move in all three directions, and that's why we have support reactions in all three directions, right? Okay, now let's have a look at this number 5, which is a single journal bearing, right? So we already saw in the last slide about the journal bearing, which allows the move in one direction and restricts the move in two directions, right? So let's say in this case, if this is your y direction and this is your z and x, let's say this is your x and out of the page is your z. So it allows the move in y direction, right? You can just visualize that, but it restricts the move in x and z direction. So that's why we have f sub x, f sub z, the support reactions in fx, the x direction and z direction, and we also have m sub z and m sub x as the support reactions for moments, right? So that's just the introduction about the support reactions in 3 dimensions. Okay, so as a general rule, if a support prevents translation of a body in a given direction, then a reaction force acting in the opposite direction is developed on the body. We already know this, right? We have been talking about this in the earlier chapters also. Now, similarly, if the rotation is prevented, a couple moment is exerted on the body by the support, as we saw here, right? This m sub z and m sub x, because the rotation is restricted along z-axis and along x-axis. So that's why these two moments, these two type of moments are there, m sub z and m sub x, right? Due to this prevention of rotation. Okay, so now coming over to the equations of equilibrium, section 5.6 of your book. So if you remember, we have talked about this earlier, that if we have a 3D system, so if we are analyzing in 3D space, then we have 6 equations of equilibrium, right? So what are those 6 equations of equilibrium? They originate from these two equations, sigma f equals 0 and sigma m equals 0, right? So the net force equals to 0 and net moment equals to 0. But once we are talking about 3D space, so we know we are talking about x, y, z space, right? So once we are talking about x, y, z space, then we can, we can take these sigma forces equal 0 into 3 dimensions, as sigma fx equals 0, sigma fy equals 0, and sigma fz equals 0, right? Sigma fx means the forces in the horizontal direction or x direction balance out each other, so there is no balance force in x direction. Similarly, there's no balance force in y direction, and there's no balance force in z direction, right? So everything equals to 0. Now, once we talk about this guy, sigma moments equals to 0, then also we can we take sigma moments in all 3 directions, x, y, and z, right? So sigma mx equals 0, sigma my equals to 0, sigma mz equals to 0, right? So moments in all three directions, x direction, y direction, and z direction equals to 0. So there's no balanced moment in x direction, y direction, or either in z direction. So these six equations are the equations of equilibrium for 3 dimensions, right? For 3D space. Once we talk about rigid body in 3D space, so we can use these 6 equations, right? Okay, so a few more points. The moment equations can be determined about any point, right? So we can take any arbitrary point and we can solve for moment equation. Usually, choosing the point where the maximum number of unknown forces are present simplifies the solution. We already know that, right? Because once we take the moment at a point where there are more number of support reactions, more number of unknowns, then those unknowns cancel out because they don't apply any moment at that point because they don't have moment arm, right? So they cancel out those unknowns, and then we can, we can determine the other unknown forces. Any forces passing through the point where moments are taken do not appear in the moment equation, as we just said, right? So this was about equations of equilibrium. We have 6 equations for 3D equilibrium, right? And how many equations of equilibrium for we have for 2-dimensional space, right? For 2D analysis. Do you remember? We have been talking about that. We have done that. We have practiced on some practice problems on that. So for 2D space, we have 3 equations of equilibrium. Sigma fx equals 0, sigma fy equals 0, and sigma moments equals to 0, right? But for 3D space, we have 6 equations of equilibrium, right? Okay. So now section 5.7 of your book. Next, let's talk about constraints and statical determination, right? So what are constraints? That's the first question. What is constraint? So we can just assume that if we have a pin support or a roller support or a fixed support, so it is giving some type of constraint to the member attached to that support, right? Or to the structure or to the body attached to that support. So that is a constraint, right? Because it's restricting the move of its attachment in some way, in some fashion, in some direction, right? So that's a constraint. Now, just visualize that when a body has more supports or more constraints than necessary to hold it in equilibrium, it becomes statically indeterminate, right? So what do you mean by statically indeterminate structure or statically indeterminate body, right? When number of unknowns is greater than the number of equations, then we call it a statically indeterminate structure or statically indeterminate situation, right? Let's say if we have this, let's say we have a beam here, right? So let's say we have a pin support here, we have a roller support here, right? So we know that we have 1 reaction here, 2 reactions here, right? So we have a total of 3 unknowns, right? We have 3 unknowns in this situation, right? And let's talk about 2-dimensional. So we're talking about 2D space. So we have 3 unknowns and we have 3 equations of equilibrium, right? So if the number of unknowns and number of equations are equal, so that is statically determinate, right? We can solve this. But at the same time, let's say if we have this, the same beam, we have this pin support, we have this roller support, and let's say we have one more, let's say pin support here, Okay, so now how many reactions? 1, 2, 3, 4, and 5, right? So we have 5 unknowns. We have 5 unknowns and we have 3 equations of equilibrium, right? So number of unknown support reactions is more than the number of equations available, right? So in this way, it is statically indeterminate. We cannot analyze this. We cannot solve this just by using statics. Of course, there are other methods, but we are not going into the details of other methods, right? At this moment, in this course, we are only talking about statics and using statics equations, right? So using equations of equilibrium, right? So in that case, once we are doing only statics equations, we are using equations of equilibrium, then this is not solvable, right? Whereas we can solve this, right? So that is statical determinacy and indeterminacy, okay? So we already talked about that a problem is statically indeterminate if it has more unknowns than equations of equilibrium, right? So that is about constraints and statical determinacy. Okay, so that was all about the theory. Now let's go over a couple of problems to see that how do we analyze 3D systems. Okay, so problem 1, we have this system where we have this rod supported by a thrust bearing at point A. This point, we have a thrust bearing and a cable BC, this guy, and subjected to a 80 pounds force, this force F of 80 pounds acting negative Z direction, right? What we need to do, what we need to find are the reactions at the thrust bearing A and cable BC, right? So we need to find the support reactions or unknown reactions at point A and the cable BC, right? So if you see here, we have x-axis here, we have z-axis here, we have y-axis here, right? Because that's the first thing what we want to do. Before we start analyzing, we need to establish x, y, and z directions. We need to establish coordinate system. Only then we can use our equations of equilibrium, right? So since this is a 3D problem, so we have 3 coordinate axes, x, y, and z, right? So now, how do we go about it? Let's talk about some steps. So first of all, use the established x, y, and z axis. We already have x, y, z axis given, so we don't need to establish our coordinate axis, and we'll use the same x, y, and z axis, which is given in the problem. Now, next thing, we all know what we need to do. We need to draw a free body diagram of the system, right? So we'll draw a free body diagram. Then we write the forces using scalar equations, right? So scalar equations of equilibrium in x, y, and z directions. Then we apply the equations to use the unknowns reactions, right? So that's what we are going to do. Okay. Now, first of all, we are already done with the x, y, z coordinate system. So the next step is the free body diagram, right? So let's draw the free body diagram. So if you remember, the at point A, we have a thrust bearing, right? So this is a thrust bearing. Now, how many reactions do we have at point A, right? Due to this thrust bearing. We know that the rod can move in y direction, but it cannot move in z direction. It cannot move in x direction. So that's why we have 2 support reactions in terms of forces, which are AX and AZ, right? AX and AZ in x direction and z direction, right? And then we have 2 unknown moments, MAZ and MAX, right? So moment around x-axis and moment around z-axis at point A. Now the other unknown is the tension in this cable BC, right? So let's call it FBC. So now how many unknowns do we have? This is 1, this is 2, this is 3, this is 4, this is 5. So we have 5 unknowns in this problem. And since this is a 3D problem, so how many equations of equilibrium do we have? We have 6 equations of equilibrium, right? So with 6 equations of equilibrium, we have 5 unknowns. So we can solve this. We can analyze this, right? We can find out 5 unknowns with 6 equations. So that's good. And we can go ahead and analyze the problem. Now let's apply the equations of equilibrium and try to find the unknown. So first of all, as there's no force in x direction, so let's apply the force equilibrium in x direction, right? So let's apply the sigma fx equals to 0. So sigma fx equals to 0. This is your x direction. This direction. This is your x direction. So what do we have in x direction, right? There's no force, right? So there's only one support reaction, that is A sub x, right? So A sub x equals to 0. So we get this one support reaction or one unknown done already, right? Now, let's apply the force equilibrium in z direction. Let's apply sigma fz equals to 0, right? So we have A sub z, this guy, which is, we assumed it acts upwards. So A sub z is a positive. Then we have FBC, this guy, again positive because it's in positive z direction. So this is FBC. And then we have a negative 80 because this guy, 80 pounds force is acting downwards, which is negative z direction, right? So we get this equation, A sub z plus FBC minus 80 equals to 0, right? So we are done with these two equations. Now let's go for a third equation. Let's take sigma moments in y direction equals to 0, right? So if you take sigma moments around y-axis, then what do you get? So we have how many moments or how many moment components do we have around y-axis, right? So AZ, we don't have any moment around y-axis. AX, we don't have any moment around y-axis, right? They are passing through y-axis. So there's no moment arm. So the only forces which are creating moment around y-axis are F, which is 80 pounds, and FBC, which is unknown, right? So that's why we get negative 80 times 1.5, which is the moment arm for 80 pounds force, right? And it's a negative because it's creating a clockwise moment around y-axis. And then FBC is creating a counterclockwise moment, so it's a positive, and its moment arm up to y-axis is 3 feet, right? So that's why we get this negative 80 times 1.5 and positive FBC times 3 equals to 0, right? So from here, from this equation, we get FBC equals to 40 pounds. And once we have FBC, we put that in this equation. And from here, we get the value of A sub z, which is 40 pounds, right? So that's how we are done with 1, 2, and 3 unknowns, right? So we are only left with 2 unknowns. So let's go and let's find out the other 2 unknowns. Now, let's take sigma moments around x-axis equals to 0, right? So we already have MAX, which is an unknown, and it's a counterclockwise moment around x-axis. So we have a positive MAX. Then we are taking moments around x-axis. So F and FBC are creating a moment, right? So this guy, FBC times 6 feet, because 6 feet is the distance between FBC and x-axis. And then we have a negative 80 times 6, because this 80 pounds is creating clockwise moments, so it's a negative. And again, 6 feet is the moment arm for this 80 pounds force with respect to the x-axis, right? So that's the equation for sigma moments around x-axis. And from here, we get the value of MAX, which is 240 pound-feet counterclockwise, because we got a positive number, right? Okay. Now, next, we'll go for sigma moments around z-axis equals to 0. And once you look at z-axis, there's no force which is creating a moment around z-axis. So it will be 0, right? So that's why we get this MAZ equals to 0. So with this, we come to the end of this problem, and we are done with 5 unknowns with the help of our equations of equilibrium, right? Okay. Let's go to the second problem, and let's try to solve this. Again, it's a 3D problem. We have this uniform plate which has a weight of 500 pounds, supported by 3 cables, A, B, and C. And we need to find the tensions in each of the cables. So A, B, and C, there are 3 cables. We need to find the tensions in these 3 cables, right? And we already have the coordinate system given, X, Y, and Z axis. The location, the directions are already given. Okay, so let's see, how should we go about this problem? So use established X, Y, and Z axis. We know that it's already given, so we will use the same given X, Y, and Z axis. Draw a free body diagram of the plate. We already know that that's the first step. After we are done with the X, Y, Z axis, we need to draw a free body diagram, right? So we'll draw a free body diagram, and then we'll write the forces using scalar equations, right? And then we will apply the scalar equations of equilibrium to solve for the unknown forces, right? So let's see. Let's do that. Okay. So here on the left side, it's the system which is given in the problem, and on the right side, we have the free body diagram. Now to draw the free body diagram, we'll take off these supports at the top, right? And or the cables themselves, and we'll replace these cables by these guys, TA, TC, and TB, right? So tensions in these cables, A, B, and C. And it was also given that the weight of this plate was 500 pounds, right? So we'll assume that this is 500 pounds weight of this plate, and naturally it will act in on the center of gravity, right? Geometric center. So what is geometric center of this plate? This plate is 4 feet by 3 feet. So this 500 pounds will act at 1.5 feet from x-axis and 2 feet from y-axis, right? So that's the point of action of this weight of this plate. Okay, and we already have this 200-pound force, the external force or external load, which is being applied at this edge of this plate, right, where it is shown. Okay, so this is how we are done with the free body diagram of this plate. Now let's apply the scalar equations of equilibrium, right? So first of all, let's take sigma Fz equals to 0, right? Because we have so many unknowns in z direction, right? So if we do that, sigma Fz equals to 0, so everything is in z direction. So we have TA plus TB plus TC all are upward, so all are positive, and then we have negative 200 and negative 500 equals to 0. So let's take this as our equation 1, right? So we take this as our equation 1, and what next? Let's take moment equation. So let's take moment equation around x-axis, right? So around this x-axis, let's take the moments. Okay, so if we take the moments, so which forces are creating the moment around x-axis? If you talk about TB is not creating any moment because it is acting into the x-axis, right? It doesn't have any moment arm. So the only forces which have the moment arm are TA, TC, 200 pounds and 500 pounds. Because they have their own moment arm with respect to the x-axis. So we'll have TA times 3, TC times 3. Both of them are positive because they are creating counterclockwise moment, right? And then 500 times 1.5 and 200 times 3, both are negative because these forces are creating clockwise moment around x-axis, right? So that's how we get our second equation. Okay, now let's do sigma my equals to 0. So we are taking moments around y-axis, right? So once we talk about y-axis, then TA is not creating any moment, right? So we have TB, TC, 500 pounds and 200 pounds. They have some moment arm with respect to y-axis. So these forces are creating moment around y-axis, right? So let's see, negative TB times 4. So TB is creating a clockwise moment around y-axis, right? So that's why we have a negative sign, and 4 is the moment arm between TB and the y-axis. Then we have, let's take T sub C, right? So TC is again creating a clockwise moment, and its moment arm is 4 feet with respect to y-axis, right? So that's why we have a negative TC times 4. Now let's talk about this 500 pounds weight. So this 500 pounds weight of this plate is creating a counterclockwise moment around y-axis. And its moment arm is 2 feet, so that's why we have 500 times 2, which is a positive, right? Because it's counterclockwise. Now let's talk about this 200 pounds force. So this is creating again a counterclockwise moment, and it has a moment arm of 2 feet. So we get positive 200 times 2 because it's a counterclockwise moment, right? So this gives us our equation 3, right? Let's go ahead and see. These are the same 3 equations which we determined on the last slide. Now let's move ahead. So we can solve these 3 equations to get the unknowns, right? So let's use equations 2 and 3, and we can use equation 2 to find TA in terms of TC, right? And we can use equation 3 to find TB in terms of TC, right? And then if we substitute the values of TA and TB from here and here, these values of TA and TB into equation 1, then we can solve for TC, right? So equation 1, we put the value of TA here, we put the value of TB here, and this is already there in equation 1. So now we only have one unknown in this equation, and we get TC equals 200 pounds, which is a positive force, so it means it's upward force, right? So this is the tension in cable C. So now we are done with one unknown, so we are left with 2 unknowns, right? TA and TB. But now it's easy because we already have these 2 equations which have TA and TB in terms of TC. So just put in the value of TC and we get TA equals to 350 pounds, again positive, so again upward force, and TB equals to positive 250 pounds, again positive, and again an upward force, right? So that's how we are done with this problem. We were required to find these three tension forces in this plate, right? Or in the cable, sorry. So we draw the free body diagram, we applied the equations of equilibrium, we solved the equations in some fashion. This is one way of solving. You can solve these equations in any way you like, right? And then you can find out these three tensions in these three cables, TA, TB, and TC, right? You use any method to solve these equations, you'll get the same answers. So you'll get the same numbers, right? So now this is the end of chapter 5, and I hope you have learned something about 2D equilibrium, 3D equilibrium, rigid bodies, how to solve the equilibrium equations, how to solve rigid body problems, and what are the equations of equilibrium in 2 dimensions, what are the equations of equilibrium in 3 dimensions, how to solve them, what is statical indeterminacy, what is statical determinacy, what are constraints. So I hope we have learned something about all these topics, about all these concepts, right? Okay, so thank you so much for now, and next lecture we'll start chapter 6, and we'll talk about the exam. So that's it.